today's lesson is the first lesson on the new unit on mathematical reasoning. You're going to need a protractor to start. So the protractor is this guy. So the first step, it says use a protractor to measure angle ACB. So you're going to take your protractor and you want to look ACB, so angle C. So you're going to take this. Remember how we measure angles. We want the C to be exactly on that T, and so you can see it. And the line CA is on the line of the 0 degrees. So here, just move this up a bit. There we go. You can see our angle is, we're going from here all the way, gives us a 90 degree. That full angle there is 90 degrees, right? This is a 90 degree angle. A little bit less, a 90 right there. So we can conclude the angle ACB is a 90 degree. As is, use a protractor. Mark any point D on the circumference of the circle. It doesn't matter where, anywhere you want. We could do it below, we can do it above. Let's put it up here. And we're going to take a ruler, and we're going to draw a straight line connecting A to D and B to D. And then what I want you to do again is take your protractor, and now we're going to measure angle D. So take your protractor, rotate it, move it up. Again, we want that 0 degrees to be on our angle, and here I could see starting from zeros right there, go around, and it goes all the way to 90 again. So a 90 degree angle, 90 degrees. Okay, repeat this process with another 3 points. Just going to erase these 3 marks here. Delete this. And delete. Okay, so I'm going to put E over here, and let's do F over there. So grab your rulers. Just draw some straight lines connecting A to E and E to B, and then A to F, B to F. And it says 3 points, right? So maybe I'll do another one down here. We'll call it G. So there's our 3 points in G. So grab your protractors. We're going to measure those points. So I'm going to measure, you have to rotate this all the way around. So we want to measure angle E. So take, line up E. Right, that 0 has to be right there, and you should get a, move it over a little bit. Oh, it's not lined up properly yet, so I've got to do some rotation. It's not moving for me, just one moment. Come on. I want the full thing. Oh, there we go. There we go. And so should show here that our angle is a 90 degree again with E. So it's coming up here at 90. So repeating that process. I'm just going to skip ahead. These should all be 90s. They even look like 90s. Now what's so special about AB? What do you notice about AB? The line AB? You should notice it's going through the center. Going through the center. So what conclusion can you make based on these observations? Well, no, what do we call a line going through the center? AB? We call it diameter. And so any angle made on the circumference of a circle whose arms pass through the endpoints of its diameter is 90. So let's write that out. Any angle made on the circumference of the circle whose arms, so those whose arms pass through the endpoints of the diameter of its diameter is 90 degrees. So what did we do here? Well, this unit is all about reasoning and drawing conclusions. And so what we noticed was a pattern, and from that pattern, we drew a conclusion. And so what we just did here was an example of inductive reasoning. Inductive reasoning. So let's look at another example. So again, we're looking at this, we're going to see a pattern and draw a conclusion. So what we're doing here is inductive reasoning. So it says complete the third step. So notice here's the original, the second one. On that new shape, we added two similar ones onto the corners. Sketch 2, again on the new shapes that was previously the originals, they added 2 to the corners. So on the third sketch, on the previous originals, we're going to add 2 of the same shape to each corner. So I'm going to have to add one right here. My drawings are going to be brutal, not going to lie. Another one. Oops. Another one. Straight. There you go. Line. These are called trapezoids. And another 2 here, and we're done. Okay. So let's, it says to fill in the pattern. So in the first one, original one, there's 1. In sketch 1, there's 2, it's number of new trapezoids added. In the sketch 2, how many new trapezoids? 1, 2, 3, 4. And in the third, we added 1, 2, 3, 4, 5, 6, 7, 8. So what pattern is happening? In each sketch, the number of new shapes is doubling. So we have 2 to 4, 4 to 8. So the fourth sketch should have 16. The fifth sketch should have, times that by 2, 32. The sixth, 64. That's how many new. So based on your table, what conclusion can you make about the number of new trapezoids? So we're comparing new trapezoids to be added in the 10th sketch. Well, the easy way to do that, there's a few ways we can look at it. You could keep adding, so 7, 8, 9, 10, and follow the same pattern. That's probably what most of you would do. Or we can actually change this to an exponent form. So notice 2 is 2 to the power of 1. 4 is 2 to the power of 2. 8 is 2 to the power of 3. 4 is 2 to the power of 4, and so forth. So notice we're comparing that to the sketch number. On the fourth sketch, it was 2 to the power of 4 new trapezoids. So the number of new trapezoids in the 10th sketch should be 2 to the power of 10, or if you continued this pattern and just figured it out on your own, or plug in 2 to the power of 10, we get 1024. That would be a lot to draw. So what is both of these example of? Well, notice we looked at a pattern, we drew a conclusion. The conclusion we actually call conjecture, and the pattern and reaching that conclusion is called inductive reasoning. So inductive reasoning, this is where a highlighter would be good, is based on, we base our conclusion on the patterns and observations. That's inductive reasoning. So here, inductive reasoning is a type of reasoning in which we arrive at a conclusion, generalization, or educated guess based on experience, observations, or patterns. I actually think I'm just going to highlight this. Might look better. So grabbing my highlighter here, let's use this one. So inductive reasoning is when we look at a pattern and draw a conclusion, and that conclusion we actually call a conjecture. The conclusion is a conjecture. So whatever generalization we come to, that's a conjecture. So those definitions should go on your study sheet. Now, just because we make a conjecture doesn't mean that it's true. It's very important to know that it could be false. Just because we make a conjecture, we look at a pattern and make one, doesn't mean it's true. So explain how you use inductive reasoning to arrive at a conjecture for part 1. So part 1, the 90 degrees, Well, we measured 90 degrees each time, and so we came to the conclusion that it's always going to be 90 degrees. So when we reason, all the angles measured 90. So we concluded, so we can generalize, that all angles of this kind would also measure 90. So we concluded that all angles of this kind would also be 90. There you go. So Bruno used inductive reasoning to arrive at a conjecture for part 2. So how did he do that? Well, he used a chart, but how did we come to this? Well, we noticed that the number of new trapezoids would double. The number of new trapezoids doubled, so we generalized that it would always double. The number of new trapezoids added doubled each time. Therefore, we extended the pattern. So we generalized that it would always do this. All right, so that's inductive reasoning. And we come to a conjecture based upon generalizing a pattern, and that's inductive reasoning. Okay, so what's a counterexample then? Well, remember we said inductive reasoning doesn't mean it's always true. Whatever conjecture we arrive at doesn't mean it's true. So a counterexample disproves our conjecture. It shows that the conjecture is not true. It shows that it's false. Another good definition to put on your study sheet. Katie and Perry were given the following number pattern. So 2 squared plus 1 is 5, 4 squared plus 1 is 17, 6 squared plus 1 is 37. They're all prime numbers. Perry's task was to see if Katie's conjecture was correct or not. So Katie made the following conclusion. When an even number is squared and 1 is added, the result is a prime number. Katie's conclusion is called so what do we call conclusion? It's called a conjecture based on inductive reasoning. We followed a pattern. She followed a pattern and made a conjecture. Doesn't mean it's true, but that was the conjecture she made. Now Perry says, I can come up with a counterexample. So let's determine a counterexample where this is false. Remember, a prime number, just by definition, is only divisible by 1 in itself. Only factor, or only divisible by, only factor is 1 in itself. So for example, 5, you can only divide it by 1 and 5. There's no other numbers that will go into it evenly. Okay, so let's try pick an even number, see if it works. Let's choose, it's not there, 8. 8's not there. So 8 squared plus 1. Well, 8 squared is 64. 64 plus 1 is 65. Is there anything that will go into 65 that is that a prime number? Can we divide it by something other than 1 and 65? And the answer is yes. We can divide it by 5. So therefore, it's not a prime number. Now, the cool thing about a counterexample, you only need 1 to disprove a conjecture. So there's our counterexample. 8 squared plus 1 is not a prime number. So it's possible to revise your conjecture. If you get a counterexample, then we can revise it to find a new one. And so any number that's not prime, it's also called a composite number. So I could have wrote here a composite number. So all numbers that are not prime are called composite numbers. Okay, so Mike and Sue were discussing what conjecture could be made regarding the prime number pattern shown below. So 3 plus 5 is 8, 5 and 7 is 12. So notice all of these that we're adding together are prime numbers. 7 and 11 is 18, 13 and 17 is 30, 19 and 23, and so forth. And they're saying this is their conjecture. The sum of two prime numbers is even number. Provide a counterexample. So provide a counterexample. Often the counterexample lies in like there's a prime number that has a very different property than every other one here. Remember, 1 is not prime, but 2 is. Okay? Pretty much every single other prime is going to be an odd number, and two odd numbers always make an even. So we need to find one even prime number, and that number is 2. So our counterexample could be 2 plus 3. It says all, no, it says all two prime numbers is going to give it even. So two odds always make an even. So 2 plus 3 gives you 5, which is odd. So there's our counterexample. So it says we can revise this, that all prime numbers other than 2 added together would give you an even number. So everyone except for 2. So the sum of two prime numbers that are not 2, which are not 2, everything but 2, is an even number. And that is a better conjecture. So make a conjecture based on the number pattern if the condition prime number was removed. Well, instead of prime number, we can say odd numbers. So the sum of two odd numbers, because that doesn't include 2, is an even number. And that is also true. That is true. The sum of two odd numbers is even. There you go. Because all those numbers up there added together, they're also odd numbers. Okay, so the last page here, Jerome investigated the following number patterns. 1 plus 2 plus 3 equals 6. He also did 5 plus 6 plus 7 equals 18. Negative 6 times negative, or plus negative 5 plus negative 4 is negative 15. Negative 12 plus negative 11 plus negative 10 equals negative 33. You notice that in all the patterns, there were 3 consecutive integers were being added together. Write 2 more numbers. So consecutive means one after another, like 1, 2, 3, 4, 5, 6, 7, 8, 9. Or, yeah. So he's like, write 2 more number patterns showing the sum of 3 consecutive integers. So we could do, no, it's not there. 2 plus 3 plus 4 gives you 9. We could do negative 1 plus 0 plus positive 1. What would that add to? That adds to 0. Okay, so what we want to come up with is how can we predict what the sum is without actually adding it together? How do I know that 1 plus 2 plus 3 is 6 and 5 plus 6 plus 7 is 18? What's an easy way to get the sum? Like, what if I gave you 123 plus 124 plus 125? I could add that together really quickly without actually adding. And how would I get that conclusion? How could we reach that quickly? Now in class, I'm going to make you figure this out on your own. But here, how does that middle number relate to the last number? Look at the middle number is my hint. Okay, the middle number. So 2 and 6, 6 and 18, negative 5 and 15. 2 times 3 is 6. 6 times 3 is 18. Negative 5 times 3 is negative 15. Negative 11 times 3 is negative 33. So we can just take the middle number times 3 would be the sum of the 3 consecutive numbers. The sum of 3 consecutive numbers is equal to 3 times the middle number. 3 times the middle number. And that makes sense because if we have like 123, 125, if I donate one of the ones to this side, then we get 124 plus 124 plus 124, or 3 times 124. Okay, so inductive reasoning can be used to make conjectures. I'm just going to use my highlighter here. Let's use yellow. Inductive reasoning can be used to make conjectures. We can never be certain that it's true, and that's where deductive reasoning is going to come in later on. So that's the thing about inductive reasoning. We can't be certain that it's true. To prove a conjecture is true, we need to use logical or deductive reasoning, which we're going to learn about tomorrow, or actually later on, next lesson. To prove that a conjecture is false, we need to find only one counterexample. That's all we need. Okay, so look at example 4. Don graph the equation y equals x to the power of x. So in our calculator, x to the power of x. So go to y equals and go x to the power of x, x to the power of x, just like so. Okay, and she wanted those windows, so window, -5, 5, and 1, and -4, 4, and 1. Okay, so this is what the window she used. After observing, she made a conjecture about the domain. So what did she make about the domain? Remember, domain is what are all the x's? So looking at this, she made a conjecture. Show that her conjecture is not true. So what conjecture would she probably make? Well, it's right there. She said that x is greater than 0. So it sure looks that way on our graph. Right? It sure looks like the conjecture here we have is x is greater than 0. Looking at our graph. And that would be a fair conjecture. So maybe if you zoom in, you could try that and see, okay. But we want to find a counterexample. So even if I zoom in, oh, did you see that little dot down there? See that little dot? It just went away. So let's look at cases that might not be, that are kind of hard to see. So let's look at 0. We'll try 0, and we'll try -1. So we'll try a couple cases. So x equals 0, and then we'll try x equals -1. So let's first try an x equals 0. So y equals 0 to the power of 0. What does that equal on your calculator? So y equals, so I can quit, we're going to try 0 to the power of 0. And that gives me, okay, it doesn't exist. So far, that fits with her domain, that it doesn't exist. So let's try -1, because remember x equals -1. So -1 to the power of -1. Remember, -1, a negative exponent really takes the reciprocal. But let's plug it into our calculator. -1 must be in brackets. -1 to the power of -1, again in brackets. And what does that equal? It equals -1. So does that fit her domain? She said that everything had to be above 0. But we tried a case of x equals -1, and it worked. So we need to change that. There's a counterexample. X can equal to, so our counterexample was x equals -1, because that's below 0. And we know that when y equals -1 to the power of -1, that was equal to -1, so it worked. That's the domain of the function. It was incorrect. So her domain was incorrect, because we provided a counterexample. So we can also say that her conjecture was false. Thus, her conjecture was false. All right, that's all for this lesson.